What I want to do today in this video is to show how to use the spectral method to solve a partial differential equation. And for this, I am going to choose a equation that is not so trivial. I am not going to do diffusion or wave equation. I'm going to do the complex Landau equation. And it looks like that. So one comment is, if you go to the Wikipedia, you're going to see something like that. This is the complex Ginzburg-Landau equation. And there is only 3 terms. In the equation that I'm going to do now, it contains one extra term, this one here. And this is going to be important because it's going to give me some special behavior. So this equation produces breeders, different kind of breeders. Some are standing breeders, some are drifting breeders. And in particular, when you make this parameter C3 is smaller than certain value, I'm going to show the figure. This is the figure. So depending on the value of this C3, if the value is slightly above this value, if we are using the appropriate boundary conditions, such as Neumann, for instance, then the breeder is going to bounce off once it hits the wall. However, when the value of C3 is slightly smaller, then the pulse is going to be annihilated. So it's just going to disappear after collision. So there is something important that happens around this value. So that's what I'm going to do around this value. And what happens is that we are going to get a pulse, a unstable solution that lasts for certain period of time. So that's what I'm going to do. So the first thing to do is discretize this equation. I'm going to show how to do that. So I start from the general method. This is a generic PDE. We have 2 terms, a linear term and nonlinear term. The linear term, the corresponding operator, contains high-order derivatives and constant coefficients. And this term here contains the rest, contains nonlinear terms, contains non-constant coefficient, etc. Now we can Fourier transform the equation. And when I Fourier transform, in particular, we are going to get here a function that depends on the wave numbers. And essentially what we have after the Fourier transform is that we are going to have an ODE, for which we can use a variety of ODE solvers, such as ODE 4.5, for instance, in MATLAB, or today I'm going to use this one, solve IVP. This stands for solve initial value problem. So this is the equation that I am working with today. This is the term that is important. That's why I wrote it in another color. So I'm going to apply the Fourier transform. Looks like that. Fourier transform for each term. And in particular for this term, the one that contains a derivative, we are going to get this thing here. So this is a second order derivative. So we are going to have a I square k square. The I square is a minus. And for the remaining 2 terms, I'm going to left the Fourier transform indicated like that in this red term and in the blue term. This one here is a W conjugate and then a Fourier transform. So that's what I'm going to do. So I go to my, let's think what we are going to do. First, I'm going to write a grid. Okay, I'm going to write a grid for my space. I'm going to define a grid. So initialize grid. And then the grid is going to have parameters, the size and also the number of nodes. And so we are going to have 2 things here. One is the space. I'm going to write it here. I think I'm going to write a node here, something like a spatial grids for space and k numbers. So this thing here is going to be a linear space. It's going to go from minus L halves to L halves. Okay, and then we have n nodes, and then something very important is because I am using spectral method, so it assumes that the boundary are periodic. So what I have to do is remove the last point. I don't want to count it twice, so I'm going to remove the last point, and point equal to false. Okay, so that's my grid for the space, for the physical space, and then Fourier numbers. I'm going to do that. So the way I write the Fourier numbers, I use NumPy FFT freq. Okay, and then you only need this parameter here. There are other parameters, but for me it's easier to remember the order of the wave numbers if I just multiply by n. I'm going to show what that means. I think that's it. I'm going to return these two numbers. Return x and k. So just to give an example what I get from this, I'm going to write some parameter here. Parameters, then we have L and N. For if I choose 2, then it's going to go from -1 to 1, and then just a few nodes. Let's print what happens here. I'm going to print x and L. No, not L, the wave numbers. Okay. K, okay. So I need K, X and K. So X and K are going to come from my grid. So I think I can run this thing. Okay. So you see, this is the interval for X. It goes from -1 to 1, but it doesn't print. It doesn't work the last node because I use this endpoint equal to false. That's what I want. And the wave numbers, first I have the positive frequencies, and then I have the negative frequencies in reverse order. This is the correct sequence to use FFT. Now I can normalize this with the size of the domain. So my domain is going to be 2 pi divided by the domain L. Oh, that's it. Okay, so now the next thing to do is a initial condition. For initial condition, I can use different things. I can use Gaussian, I can use different things, but the one I want to use is a Sech. Sech looks like that. It's just a bump. Sech. So that's what I'm going to write. Let's see. So I'm going to use a function for this. I'm going to call it initial condition. And this is going to have as parameters only x. And this is very simple. Just write the function. So it's going to return a Sech on x. And that's it. Except that we need two things. First, we need an amplitude. And also in Python, we don't have Sech. I don't know why we don't have Sech. But instead of Sech, I can use the inverse function. I can use a hyperbolic cosine. And then instead of multiplying, I'm just going to divide. So dividing by cos h is equal to multiplying by a sech. The other thing is that this amplitude could be 1, could be just 1. But in previous, I worked out already this problem, and I realized that if I use 1.1288081, I get better results. So that's why I'm going to use this amplitude for the initial condition. So I think that's it. I have my initialization, I have my initial condition. Now I have to solve the problem. I have to advance this initial condition. And to advance the initial condition, I'm going to use a library of solvers. I'm going to use from SciPy integrate. I'm going to import this solve initial value problem. That's the function I'm going to use. Okay, so I'm going to use here. So I'm going to write a function for this. Def solve complex Ginzburg-Landau equation. And this is going to have several parameters. There is going to have the size, it's going to be the number of nodes, and we have, of course, a time span, Tmax. We are going to have also a time step. This is not really time step, this is time interval at which I want to get solutions. It's not a time step because we are going to use a optimized solver which uses a adaptive time step. So typically for this time interval, I'm going just to choose 1. Okay, so now we need to solve the partial differential equation. I'm going to use this solve IVP. And this solve IVP is going to need the equation. I'm going to write here function for the solver. So notice here the following. This function has to be written as a function of t and y only. So I need to write my function in this form. Okay. So in addition to the function for the solver, I need also the time span. Time span I'm going to choose from 0 to Tmax. Then I also need the initial condition. Initial condition. So we are doing a spectral solution. So this initial condition is going to be in the spectral space. So in WT initial. Okay. What else? We need also the method. I'm going to choose what is suggest here. Method is going to be equal to Runge-Kutta 4.5. This is similar to ODE 4.5 in MATLAB. And what else we need? We need t-eval. T-eval is an array of times at which I want to get results. I'm going to write that thing later. Okay, I think that's it. That's all I need. So now I have to write all these things. I have to write the t-eval. This is t-eval. I have to write the initial condition and the function for solver. So let's start with that thing first. The function for solver. Def function for solver. And this, remember, has to be function of t and y only. So I'm just going to write it just like that. Return this is going to be my function. This is going to be the left-hand side of this equation here, the right-hand side of this equation. So this is going to be complex Ginzburg-Landau equation, right-hand side. And this is going to have more parameters. This is going to have the time, y, and also n. This n is important to account for the number of coupled equations, and then my k squared, this one here. Okay, so I have to write that thing. So I'm going to make a note here. This is function for complex Ginzburg-Landau equation. The right-hand side of complex Ginzburg-Landau equation. Okay, so what else I need here? I need the initial condition. I'm going to write that thing. Initial condition, WT0. This is going to be equal to I have to enter my initial condition and then Fourier transform this initial condition. So I'm going to take n pi FFT and then FFT initial condition. Okay, that's going to be the initial condition. Okay, and then what else? I need my W0. W0 is going to be, wait a second, I think I have to write this thing outside of this. No, I think it's correct. Let's see. So let's see if I write my initial condition as I'm going to call this part here. Yes, I think I have to write this thing outside. Function for solver should contain only this part here. Yes, because I don't have more parameters here. So it's better to write it outside. Let's see. Okay. So I have my W0, initial condition from there, then Fourier transform the initial condition, okay. What else I need? I think I need the time eval. Let's write the time span. Time eval is going to be equal to what? This is just a time interval. So I'm going to use MP range from 0 to Tmax, and with this time interval. So the thing is that This is going to give me an open interval. If I want to include the last value, I have to make a plus dt. Okay. So let's see if this thing works. Solve. I need to close this function here. So what I'm going to get from the solve is going to return what the solution in x. This is going to get the solution. Okay. What else? I think I want to know why this is great. Okay, I think that's it. It was just the indentation. What the problem was, the indentation. Now it looks correct. So t-eval. This is t-eval. Okay. So I think that's it. Let's see if this makes sense. So you have the initial condition, then WT, Fourier transform the initial condition. This is going to go there. Then t-eval is going there. Function, we still have this function for solver is here. The k numbers. Initial condition and k2. So this initial condition comes from there. We need also to grid. So we have the grid from there. So by the way, I am also going to use the k square. So I'm going to write it here. K square is going to be equal to k square. And I'm going to get the numbers k squared there. So I'm going to write it here. So x, k, and k squared are going to come from this function. And now it makes sense. Yes, now it's okay. X and k2. This is just the time span. Okay. Yeah, I think that's all I need. Okay, so this is the complicated part, but I think is correct. So now I'm going to write this thing here. I'm going to write my equation. And that's not difficult. I'm going to do it somewhere here. Then write my equation. So instead of y, the equation is for wt. This is, stands from Fourier transform of w. So for this I need several things. I am going to write this equation here. I am going to write the parameters. So just write parameters. So we have C0, C1, C2, C3. And I'm going to take the values from the paper. Let's see, are here. Is 1 minus 0.5 and 1.1. So 1 minus 0.5, 1.1. And now C3 is here. Okay, this is the value for C3. So one comment here is that I already worked out this problem, and I noticed that if I use a few more decimals here, I'm going to get a better result. I'm going to get a standing breather that lasts for a longer time. So instead of 29, I'm going to use 28, 61, 586. That way it gets me a much better time breather. Okay, so what else? Just write the right hand side of the equation, this expression here. So I start 1 plus IC0. So right hand side is 1 plus IC0. I in Python we write 1J C0, then times WT here. Then the next one is 1 plus IC1, 1 plus IC1, and this multiply what is multiply this thing here, minus k squared W transform, minus k squared multiplied by W transform. Okay, and then one more term here is going to be minus 1 plus IC2 minus 1 plus IJ C2. This is not IJ, this is 1J. Okay, that's my I. What else? We need another term. This one here. Wait, I have to write. This thing here is a non-linear term. Just going to write that thing. Non-linear term. I'm going to write that a little later. Then C3. C3 multiplied by this complex conjugate term. And I'm going to write those, the nonlinear and the conjugate term here. So nonlinear equal to what, and then the conjugate term equal to what here. So how to get those? I'm going to show how to write this part here. So I just write what is written here. So I have my W, then take the absolute, then multiply by W, and then I take the FFT of this thing. So I'm going to take FFT. FFT, okay. I think that's it. This term is square, so I have to write here square. Okay. Now the conjugate, something similar. I'm just going to take conjugate and then FFT. So I take conjugate of W and then This conjugate is a is a NumPy function. And then FFT. That's it. Now, when we initiate this program, we are going to have WT. So what we pass to the to this function is a WT. So I need to inverse Fourier transform to get my W. So the W is going to be MP FFT inverse Fourier transform of the WT. And I have to write a note there to remind that I'm going to recover W. Recover. Okay. Let's see if this is correct. I think it's correct. Nonlinear. Okay. 0, 1. 0, 1, 2, and 3. Okay. I think it's correct. WT. Oh, wait a minute. This is the first term, is WT. Second term is also WT. Okay. Nonlinear C3 conjugate term. Okay, I think it's correct. Now we are going to return this thing. Return right hand side. So there is no errors. So this thing should work. We can try to see if it works. Okay, so let's see if it works. So this sol is going to get me what? Sol and x. Sol and x. Okay. I need these things. I'm going to choose Tmax, just a small, maybe 10, and then dt, just a simple interval. Let's say 1. Okay. Just to have an idea what I'm getting here, I'm just going to print the shape of these things. Print, then sol. So solution contains two things: contains the time interval and contains the solution. So I want to check everything. So let's see this shape, and then shape, and then for the solution, and also the x interval, x and x. Okay, so I'm going to run this thing to see if it works. So there is an error here. Let's see. I see. X is not inside solution, so only like that. Let's run again. So I think it looks like it's working. So X is a array of with 8 nodes. Then time also is an array. It contains 11 nodes. That's what I want. And the solution, it has 8 rows and 11 columns. So it has 11 columns, one for each time. When I plot this thing, and I have to transpose this solution, because what I'm going to do is Fourier transform each row. So I need to transpose this thing. And I'm going to write now a function for to plot this thing. So we have here 2 dimensions. We have the time and also we have the space. And the solution is the third dimension here. In particular, we are going to plot the absolute value of the solution. So we need to plot something like a contour plot to see how it looks from above. So let's write a function for this. I'm going to write my function, for instance, here. This is going to be very simple, just a simple contour plot. Plot contour. And then we are going to need the solution. We are going to need the array, and then also the size. So how I do this? So remember, we are doing a spectral solution. So what we have here is the solution in the Fourier domain. So I have to inverse Fourier transform the solution. And I'm going to do that row by row. So I'm going to do a for loop for WT in solution Y transpose in such a way that I transpose this thing to have 11 rows and 8 columns. Each row corresponds to each time. So that's what I'm going to do. Fourier transform. So my W is going to be equal to numpy FFT inverse Fourier transform WT. So after I inverse Fourier transform, I'm going to put each result into a new row. So I'm going to open a list here. A list of snapshots. So each snapshots correspond to each time. Snapshots. So just an empty list there. And then I'm going to append each new row into this snapshots list. I'm going to use snapshots append W. Now remember, W is a complex number, so what I want to plot has to be real, and in particular I'm going to use the absolute, and absolute is a numpy function. Okay, so I think that's it. Okay, so I think that's all I need. Another thing very important is that because I am processing each row, so what I get after at the end of the for loop is a list. And if I want to do vectorized operation, like for instance computing the contour plot, I need first to convert the list of snapshots into a numpy array. So I'm going just to rename the type of the snapshots array. So the snapshots array is going to be equal to a numpy array of snapshots. I think that's it, just to make sure. At the end I'm going to print the shape of that. Print, so snapshots shape equal to snapshots shape. Okay, so I think that's it. Now I can plot my figure. So let's create a figure. I'm going to PLT. This is just to open a figure. Then my contour plot, PLT, contour. I'm going to use contour F. This stands for fill, not fill, is a FILL, contour fill. And okay, one more thing here is that now is the array for the snapshot is vectorized, so we need to use two-dimensional arrays for X and for the time. I'm going to write those here, but just let me finish this command there. So it's going to be the snapshots. Then, because this is a contour plot, we need a number of levels. Levels equal to 10, for instance. And now I have to write the matrix for X and the matrix for the time. X and time are going to be equal to here is very simple. It's the same function that we use in MATLAB. It's a mesh grid. So NumPy mesh grid what X, they are my array, and the time we can take that from the solution. That's it. And then I have to show my figure. PLT show. Let's see, I think that's it. I don't see any errors here, so that should work. So just let me review this function to see if there is any mistake. I open the snapshots, okay. This looks correct. I change the type from list to a NumPy array here. Okay. Yeah, looks like it's correct. So let's see if it works without any errors, and then we are going to give it more appropriate parameters. So I'm going to run it. Okay. Where is the figure? There is no figure because I need to call the function. Okay, so let's call this function. So by the way, I'm just going to rewrite this a little bit better. Going to write function for this. And then, okay. Then run my main. Okay. Now it looks better. Okay, so after I get the solution, I'm going to plot. So let's see if it works. Yeah, looks like it's working. I need to change this color scheme. I don't like green, and also I need to, okay, let's first do something more interesting. So instead of 2, I'm going to get 64 and then 128, for instance. No longer solution, 150. Then I want to also change the color scheme here. CMAP Inferno. Okay, so let's run it. Okay, yeah, it's working. So we have my two standing solutions that remain stationary for some time, after some transitory period, of course. So I'm just going to cut this part here off to show only the part that I want to show. And also I'm going to reverse this because it's too bright. So instead of plotting the absolute value, I'm going to plot the minus absolute value here. And let's modify a little bit my contour plot. So where can I do here? I think first I'm going to add some axes. Plot x it's not x-axis, it's limit. This is from minus L halves to L halves. And then the same for y. Y limit is going to go from 40, okay? I'm going to cut the transitory period to the end, and the end is solution time, the end of that array. What else I want to do here? Maybe adding a color bar. So I'm going to add a color bar here, PLT, color bar, my plot. And my plot is going to be this thing here. Okay. Yeah, I think that's it. Let's see if it works. Color bar. There's a typo there. Okay. Yeah, it looks okay. Not too bad. So what we have here is a quasi-periodic standing breather, and we have a spectral solution for the complex Ginzburg-Landau equation. And I think with this I'm going to stop this video.